talked so far about, we had a product rule, that right, if we, choosing something means making two independent choices, then we can just multiply the number of choices that we have to get the total. We also talked about an addition rule, right? If, like, well, choosing this means I either have these choices or I have these choices and they don't overlap, we can add. And we also talked about subtraction, where if there is some overlap, we just have to subtract off the part that overlaps. Some examples of that. So obviously the only thing that we haven't talked about is division. And there isn't indeed a division rule. That's what we're going to talk about today. And so as a motivating example, I want to go back to our scenario with different kinds of soup. So, so we have, 10 different soups as before. And we want to, eat soup for 4 days. Okay, and we saw before, using the product rule that, if we want to know kind of how many different schedules we can make for ourselves, we can say, well, we have 10 choices for the first day, and then after that there'll be 9 choices we have for what to eat on the second day, and so on. So there's 10 times 9 times 8 times 7 schedules. Okay, but what if the only thing I really care about is which 4 soups I'm going to eat? I don't actually care about which I eat on which day. Let's just say I have 10. Maybe I'm going on a 4-day trip, and I have 10 soup and cans of soup, and I just want to pick 4 to take with me on my trip. And I don't really care. I'll just, each day of my trip, I'm just going to get them out and just eat whichever one looks the best. It doesn't matter. But I want to know how many ways can I choose 4 of these soups, and I don't care about what order. And obviously this is too big, like this is too many, because that says, well, if you pick, pumpkin soup and then chicken noodle, that's different than choosing chicken noodle and then pumpkin. But I'm saying now, I don't care, right? Those are the same. So what if we don't care about the order? Right, we just want to pick a set of 4 soups. Right? In other words, we could say, what we're asking now is, how many different subsets of exactly 4 things are there that I can pick out of a set of 10 things? So in other words, how many 4-element subsets are there of a 10-element set? So that's our motivating question. And we're going to come back to this. We're going to be able to answer this in a little bit. But first I want to explain what the division rule is, and then we'll look at a simpler example or 2, and then we'll come back to this one. Talk about this one. So here is the division rule. So I'm going to say, suppose we have n total choices, but we want to think of some of them as being the same. In other words, I've got all these choices, but some of them I don't care. I don't actually care about the difference. Just like with the soup, I didn't care about the difference between picking chicken noodle and then pumpkin, or just pumpkin then chicken noodle. It's like, okay, those are technically different, but I don't care. So we'll say, but we really want to think of some of them as being, let's say, equivalent. Okay, so there's one very strong stipulation though. If the choices number of, I'll say, really different choices is n divided by k. All right, one way we can think of this is if we draw a rectangle. So the idea here is, I've got a whole bunch of, so each box represents some choice I could make. But I'm saying, all the boxes in a given row I want to think of them as all the same, right? So all the choices on a row are equivalent. Okay, and so of course, if my total is, if I have n things total, and there's, right, so each row has exactly k things in it. So each row is k different choices that are all the same to me. Then obviously, how many rows are there? There's n divided by k. The total is n, and there's k things in each row, and the number of rows is n divided by k. It's important, this stipulation, that they always come in groups of exactly k, because otherwise division doesn't really make sense. If it's like, well, these 2 choices are the same, these 6 choices are the same, these 17 choices are the same, I can't do any kind of division to figure out how many there are. But this happens fairly often, where it's like they come in groups that are all the same size. The reason why is kind of deep, and I don't want to go into it, but trust me, this happens a lot more often than you would think. You might think, like, oh, it's a really special situation that they're all exactly the same size. No, it actually happens fairly often. Essentially, it's when the things are all the same, have to do with some kind of symmetry. And it's like, well, if you flip things this way, it's always the same, or whatever. And that tends to make things be all the same size. Okay. So let's do it. So here's the question I want to answer. How many ways are there to seat 5 people around the table if we only care who is sitting to the left and right of who? Right. In other words, what I don't care about is which actual seat you are sitting at. Right? If you have a certain person on your right and a certain person on your left, it doesn't matter if we all change seats, but I end up sitting next to the same people. To me, that's the same. It may not be the same. Depends on maybe the seats are not all the same. But in this example, let's suppose it. Well, so first of all, we can say, okay, well, forget about the second part where we don't care about what actual seats people are sitting in. What if we do care about that? How many ways are there to seat 5 people at a table? That we know how to answer. And it's similar to, like how many ways there are to eat, make a schedule of soups. Because you can say, well, who's going to sit in this seat? There's 5 different people I can choose to put in this seat. Once someone's in this seat, who am I going to put in the next seat? Well, there's 4 people left over that I could put in that seat. So that's 4 choices. 3 choices, 2 choices, 4 choices. So the total number of ways to seat people is 5 times 4 times 3 times 2. So like if I put, you know, if I put the 5 people in a particular order, if I had everyone stand up and move 1 seat to the right and then sit back down, right? That would be different according to this, because I put the different person in seat 1 and a different person in seat 2. But we don't want to think of it as being different. We want to think of those as being the same, right? I could then have them get up and move another seat to the right and sit down, and that would also be the same, right? In fact, I can keep doing that, and you can see that there's, you know, for any particular order that the people are in, there's 5 different ways I could rotate them that we want to consider them all being the same. Does that make sense? For every particular, or let's say, how do I want to say this? I'll just say every particular seating is equivalent to 4 others. Right, there's like 5 total rotations. We should do. Okay, so therefore, by division rule, there are, well, it's 5 factorial. That was the total, but I want to consider some of those the same, and they always come in groups of 5. 5 things are the same, so I divide by 5, which is 24. So it's 4 times 3 times 2 times 1. 24 ways, or I'll say unique ways to see. Or, you know, as a further example, what if I also didn't care like which side of me people were sitting on? So if I'm sitting next to the same 2 people, I don't care whether they're sitting on my right and left or my left and right. If everyone is sitting next to the same 2 people, then I also want to consider that equivalent. In that case, we would just have to divide by 2 because we would divide by 2 more. We already divided by 5. We would have to divide again by 2 because, you know, and you have to think about this a little bit to convince yourself of this, but you can always kind of like think about like putting a mirror up to the table and like everyone flips who's on their left and right, and that's the same. So you'll always come in those 2s. Anyway, so let's move on. Right. Another way to see this would be to say, well, so I mean this is using the division rule. There's actually another way we could come at the same answer without using the division rule. For this example, which is where we say, well, person A has to sit somewhere, and it doesn't really matter where they sit because you know whatever seating I had, I could just have everyone like stand up and rotate until person A was sitting in a specific spot. So let's just say that person A always has to sit in seat 1. And then from there we could say, all right, well given that, now we have 4 choices for who to put next to them, and 3 choices for who to put next to that, and so on. So it would give us, so like person A is kind of fixed. We don't get to choose. They always have to sit in that 1 seat. And then from there we could say, well, there's 4 choices and 3 to 2. So we come up with the same thing. Okay, so let's go back to the soup example. So again, how many ways can we choose times 8 times 7 orders we can put, or yeah, I'll say schedules, right? But some of those schedules are the same. And the question is, you know, how many, if I pick a particular schedule, how many other schedules are, I want to consider the same as that? So, if I pick 4 particular soups, and I put them in some schedule, right? I can take, if I just keep those same 4 soups, I can put them in any order that I want. And those will all be the same, right? So the question is, if I have 4 soups, how many different orders can I put them in? So what do you think? So again, in other words, if I want to stick to, if I have 4 specific soups in mind and I wanted to stick to those 4, right, how many different schedules can I make that only use those exact 4 soups? What? That divided by 10. No. That would be way too many because, like I'm just sticking to these specific 4 soups. I'm not letting myself choose anything other than those 4. So, like these numbers are like I can't choose among 9 things or whatever because I only have these 4. So I only have 4. How many different orders can I put them in? Yeah. 16 or 16. Okay. So I don't remember. Okay. Yeah, that's right. For the same reason, right? If I have 4 things and I want to put them in an order, then it's like, well, I have 4 ways to choose which thing to go first, 3 ways to choose what goes next, and then 2. So, we've got, for any 4 given soups, there are 4 factorial, plus 4 times 3 times 2 times 1, different orders I can put them in. I should say we. Right, but all of those orders, I want to consider them equivalent. Right, because I actually don't care about the order. Right, so given the same 4 soups, any order that they're in, to me, that's all the same. So, I'll just say which we want to consider equivalent. Okay, but that's exactly what we need to use the division rule. So this is saying, look, whatever 4 soups you pick, there's always going to be exactly 24 factorial different orders you can put them in that are all considered equivalent. So what we really need to do is divide by 24, because we've kind of, each thing that we really care about, we've counted 24 times. And we've counted like 24 different orders that we know. So, on the division rule, 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1, which is 4 and the 2 cancel with the 8, and the 3 cancel with the 9. So this is like 10 times 2 times 7, so 210. The actual number doesn't matter so much. The important thing is kind of this expression that we got. Because I want to generalize this now, right? This doesn't apply only to numbers 10 and 4. So more generally, if we want to pick a subset of k things out of a total of n things, okay, let's think about how to do this more generally. So first of all, we saw in last class or 2 classes ago, I don't remember, you know, the number of, if we care about the order, right, then it's like n times n minus 1 times n minus 2, but we don't go all the way to 1, we stop it after we've done k things. We only want k. So there are n times n minus 1 times dot 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 times, n minus k plus 1, which we could also write as n factorial divided by k factorial. That's the number of orders in which, or which to pick k things. Sorry. That's not k factorial, that's n minus k factorial. Yeah, because we go, we have k things here, so we go from n down to n minus k plus 1. And then we want to cancel everything from n minus k onward, we cancel, so that's why this is 10 minus. Okay, but that's, that's kind of like 10 times 9 times 8 times 7. That's too big. That has lots of different orderings for things, and we don't care about the order. So for any particular choice of k things, right, there are, well, every time we have k things and we want to say how many orders can I put them in, that's just k factorial. There are k factorial say orders they can be put in, which should all be equivalent. So therefore, by the division rule, the number of subsets, or just the fact that I'm using the word set implies that I don't care about the order, right? The number of subsets of k things out of n is, well, it's it's this divided by this. I'll say this is number 1, this is number 2, is 1 divided by 2. That is, well, let's see, that would just be n factorial divided by factorial times. This is another one of those formulas that you can in theory memorize. And if you use it enough, you'll probably just start to remember it, but I definitely would like you to understand excuse me, where this comes from, right? So you could, in theory, rederive it if you needed to. So, sorry, any questions about this first? as an aside, there's something I find very interesting about this. Well, there's a lot of things I find interesting about it, but one is, I mean, if I just write 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1, like, how do I know that everything's going to cancel? Like, what? Like, maybe I'd end up with, 15 halves or something. Like, the 2 didn't cancel, and I get a fraction. If you just look at this, it seems kind of magical that, like, everything down here, there was something up here that I could cancel it with, and everything on the bottom finally canceled, and I was just left with some numbers in the top. Well, I mean, it still might seem a little magical, but we know it's going to happen because we've just argued why this actually counts the number of choices of something. So it has to be an integer, because the number of things you have can't be like a fraction. So it has to cancel. Like, everything is going to cancel because it counts something. I don't know. It's like, how do the numbers know that they have to cancel? I just, somehow it seems magical to me. But that is a valid argument. If someone's like, how do you know that everything's, when you do this formula, how do you know that everything on the bottom is going to cancel with something on the top? It's like, well, because this formula, we argued why it tells us the number of something, therefore it must be an integer. Therefore everything's going to cancel. It seems kind of cheating, but that is a valid proof. All right. So this is so important. This idea of like picking a subset of some size out of a bigger set and like knowing how many of those there are, that comes up all the time. And it's so important that actually like this has a special symbol and is used for it. So this is actually called a binomial coefficient. And I'm not going to tell you right now why it's called that, but maybe we'll see why later. And so let's see. And we use the notation. So we put big parentheses with like an N and K like this. And we pronounce this like this symbol here. We pronounce it N choose K. Right? Because it tells us the number of ways to choose a set of K things out of a set of N things. And you really do just write one number or variable or whatever over top of the other, and you just put them in kind of big parentheses. And this is completely standard notation. Like, any mathematician, if you wrote this, they'll know exactly what you mean. So we've got some time. So I think what I want to do. So these are really, really interesting. They have a lot of patterns that show up. They're used in a lot of places. So what I want to do to start is we're just going to make a table and start filling in some values of this and just kind of playing with it and seeing what patterns we notice, seeing if we can understand why we see those patterns. Okay. So I'm going to assume, let's see, make it a page. Let's put it up there. But we're going to make a little table here. So this is going to be a table of inches. So here's actually, you know what? Yeah, there we go. Nice. All right. So start filling in some things. So we'll probably do a few together, and then I might ask you, like, maybe we'll just, like, we can work on different ones and then throw them out. So how about, let's fill in this one. How about 0, choose 0? So some of them might not even make sense, right? So we can see whether this even makes sense. So, and we can think about it from 2 points of view. We can think about it, both we can use this formula and see what we think the formula would be equal to. We can also think about what it's supposed to mean in terms of how many ways to choose a certain subset out of a bigger set, and what we think the answer ought to be. So what about if I put, if n and k are both 0, what does this formula give me? Does that make sense? What would I get? 1. 1? Yeah. Because 0 factorial is 1. This is 0. It's all 0 factorials everywhere, and I just get 1 divided by 1. Okay. Does that make sense? So this is saying if I have an empty set, how many ways can I choose a subset which is also empty out of that set? Sure, there's one. The empty set is a subset of the empty set. And I don't really have any choice in the matter, right? There's only one way to get an empty set. So, sure, that actually kind of makes sense. That should be 1. Okay, so, there. So, 0 is 0 factorial over 0 factorial, 0 factorial. What about this one here? So this one here would be 0, choose 1. So n is 0 and k is 1. What would I get in that case? This one would I get? So again, n is 0 and k is 1. Still be 1? How did you get that? It turns out, if you use complex analysis, there is a way to extend the factorial function so that it makes sense of negative numbers. And you get like weird things called like pi and square roots and stuff. We're not. So no, you cannot take the factorial as a negative number. So yeah, so because if n is 0 and k is 1, this would be 0 minus 1, you get negative 1 factorial, which doesn't make sense. So we would have to say that doesn't make sense. Does it make sense that that doesn't make sense? I see some nods. Why?
You can't make a set out of more things than you have.
Right. Exactly. If I'm trying to pick a set of size 1 out of an empty set, I can't do that. Right? It's not possible. So actually, we're just going to say, you know what? We're just going to say in that case it's 0. Like, so we'll say, forget about this formula. We're just going to say, look, if k is bigger than n, we're just going to say it's equal to 0, because there's 0 ways to choose a set of that size out of a smaller set. Right? So, the answer is 0. So, in fact, right, everything like from here on over, this is just all 0, right? Because here's like n is 1 and k is 2, or k is anything bigger, right? These are all these places where k is bigger than n. We're just going to say everything up there is 0. So let's forget about that. Okay. How about when n is 1 and k is 1 and k is 0? So n is 1, k is 0. I'm going to get 1 factorial on the top. Down here I get 0 factorial. 1 minus 0 is 1 factorial, so it's just, again, 1 divided by 1 is all 1, right? Does that make sense? Sure. If I have a set of one thing, but I want to choose an empty set, yeah, there's only one way to choose an empty set. Okay, how about when n is 1 and k is 1? Well, this is just going to be, 1 factorial, 1 factorial, 0 factorial. Again, it's a bunch of 1s. You get 1. That also makes sense. If I have one thing, and I want to choose one thing, there's one way that I can choose the one thing that I have. Yeah, here.
It would be 1s all the way down.
Okay, it would be 1s all the way we're choosing an empty set, and there's only one way to do that, to not choose any of the things. So that should be 1. We can also think about the formula. If k is 0, that means I'm going to get n factorial on the top. This is going to be 0 factorial, which is just 1. And n minus k is going to be n. So we get n factorial on the bottom. The n factorials will cancel, and I'll just get 1. Okay. So that makes sense? So these are all 1s. So we'll say, I'll just write that over here to record. I'm going to record just kind of some properties, general properties that we're figuring out. So n choose 0 is always 1 for any n. Okay. So here's what we're going to do. Let's only go up to 5 for now. If you start getting bigger, it's just the numbers get really big. But for now, let's go up to 5. Everyone, just like pick a random, like, so here's all these squares that we haven't filled in, right, from here up to 5. Just pick one of them at random and see if you can calculate what the number should be that's there. And then when you figure it out, tell me and I'll fill it in, okay? I'll put the formula over here so we can see that too. Don't feel like, if everyone picks like something right here, they're like, oh, this is the most random spot, like right here. I mean, someone has to do this one, and someone has to do it. So hopefully whatever ones are left, we can then fill in. We can also do several if we have time.
I did 4, 4.
Okay, 4, 4. What did you get?
1.
1. Okay. What else, Mason? Did you get?
I did 4, 2.
4, 2.
6.
6. Okay. Olivia?
I did 3, 2,
3, 2.
and I got 3.
3. Okay.
I did 5, 5, and I got 1.
5, 5. You got 1. Okay. Garrett?
I got 5, 3. I did 5, 3, and I got 10.
Okay. Any others that anyone has done so far? Yeah, JC.
2, 2, 1.
2, 2, you got 1, okay. Yeah.
3, 3 is also 1.
3, 3 is also 1, okay. Noticing a pattern there. One. So you mean 2, 1? Yeah, 2, 1 is 2, okay. Yeah.
I did 4, 3, and I got 4.
4, 3 is 4, okay. JC.
3, 1. 3.
Okay. One more to fill in. Or 1 is also 4, okay.
Yeah. I think I would guess, I think 5, 1 is going to be 5.
Okay, what tipped you off?
Because well, 1 is pattern.
Yeah.
So it's like 5 factorial divided by 1 divided by 4 factorial, it would just be
Cancels
5.
everything but the 5, yeah, okay. Give your hand up, please.
No,
do you all think 5, 4 is going to be? Probably 5. One more. It's 5, 2.
All
5,
good.
5, choose 2. You get 10. 10. Anybody else get that? Okay. Here, I'll fill in the next row for you. I just know what they are. So what patterns do you notice? I mean, we already noticed a few, I think. Here.
Because for 5 choose 2 and 5 choose 3, because of 2 plus 3 is 5, they're the same numbers k and minus k. So it's essentially the same thing on the bottom. That's why you get 10 for both of those. And so that would be the same for 3 choose 2 and 3 choose 1. It's right there the same because 2 plus 1. That's, yeah.
Okay, so you're saying, like, you know, in this example, like 5 choose 2 equals 5 choose 3. Because if you do the formula, in both cases you get 5 divided by, like if k is 2, then n minus k is going to be 3, and vice versa. If k is 3, n minus k is going to be 2. So it's always equal to 5 or 2. Okay. I agree. So that explains why like these two are the same, and you said like why these two are the same. Like, can you generalize that at all? Are there more things that have to be the same by that a similar kind of argument?
N over k is always going to be equal to n over n minus k.
Okay, so you're saying n choose k is equal to n choose n minus k? So you don't think that makes sense? Well, so of course n choose k is equal to this. What is n choose n minus k? Well, if k is n minus k, I'm going to get n minus k factorial here, and here I get n minus k, which is k. The n's cancel and they just get. So yeah, that looks like that's always, so that looks like that's true by looking at the formula. What does that mean about this picture? So like we saw that, you know, here's 5 choose 2 and 5 choose 3. Here's 5 choose 1 and 5 choose 4. Right? Here's 5 choose 0 and 5 choose 5. Right? And this is saying those are like, these are the same, these are the same, these are the same. Right? So this is actually telling us that each row is going to be like a palindrome. Right? It's the same forwards and backwards. In terms of what it means, here's a way to understand this. So why would it be the same? Why would I have the same number of ways to choose a subset of k things out of n as choosing a subset of n minus k things out of n? One way to think about it is, I can either think in terms of the k things that I want to choose, right? How many things are going to be left over if I choose k things out of n? N minus k, of course. So I can also think of it in terms of choosing the things that I want to be left over. I have the same number of ways to choose the k things that I want as there are to choose the n minus k things I'm going to throw away. It's the same. You can also just think of it in terms of, really what I'm doing is taking my set of n things and splitting it up into two sets. One of size k, one of size n minus k. And it's the same. Same number of ways. we also see these ones all along here. Which again, like, well, this is, since we already knew that this is all ones, these have to be equal to those by this thing. Also, you know, what do these mean? It's like 4 choose 4, for example. It's like, well, how many ways can I choose a subset of 4 things out of my 4 things? Well, only one, because I just have to choose all of them. Right? So we'll talk more about this. This is called Pascal's triangle. It's very famous. Pascal's triangle has another very interesting property, which is, and you probably didn't notice this just by looking at this, but if you look at every cell is the sum of the cell above it and the cell above and to the left. So like 5 plus 10 is 15, 10 plus 10 is 20, 4 plus 6 is 10, 1 plus 3 is 4. And so
that's why all of that's 0. It would have to be 1 plus 0.
Yeah, that's one reason to make that all 0, to make that work. You're right. So this is actually telling us, in terms of binomial coefficients, we can say n plus k equals n minus 1 choose k plus n minus 1 choose k minus 1. And I will let you think about, so we could prove this, you know, by using the formula and doing some algebra. It's not too bad. You have to like factor some things out and, you know, whatever, distribute and stuff. There's also a way to understand it sort of combinatorially by thinking about what this means. Like, why would it, you know, this is kind of saying like, well, to choose k things out of n, I can kind of break it down into like, well, I can either do this or I can do that, and then I add them together. I'll let you think about that. It's a nice little exercise to figure out why that makes sense. All right.